get a hinge loss of xy on our model theta. This is like the standard setup for SVM. To make it a statistical learning problem, let's assume that there's some unknown distribution D over labeled pairs. And we're going to get labeled data, x1, y1 up to x and yn, which are all drawn from this distribution D, except perhaps in epsilon fraction of these samples are adversarial. So this is just a robust setting. Okay? And now our goal is to just minimize our loss on fresh data, or equivalently, in this setting, simply minimize our expected loss from new samples from this distribution. So this is just minimize R of theta, which is the risk. Okay, so hopefully this is all fairly standard stuff. But we can drastically generalize this actually. There's nothing really special about SVM here. Really, when we get labeled data from this distribution, all we're getting are these empirical loss functions, right? These empirical loss on the current data. So what we can think of is really we're getting some distribution over functions, namely these empirical loss function. And we get samples from this distribution over functions. We have functions f1 through fn drawn in this distribution, but again, in epsilon fraction of these could be potentially adversarial. And now, finally, our goal is, instead of just minimizing the expected loss, we can just think of minimizing the expected function. So this is just a standard setting for stochastic optimizations. Hopefully this makes sense. If it doesn't, please say something, because this is what we're going to be talking about. So, okay. So hopefully this is standard. I should say this really does capture a lot of settings. For instance, it captures SVM, obviously. And it also captures stuff like regression, logistic regression, learning neural networks, and so on and so forth. A lot of very standard supervised learning tasks. And this has been studied. The problem of studying this problem with this data poisoning has been studied in many variants in the literature all over the place. Okay? In this work, we're going to focus on a new framework for this problem, which achieves the following guarantees. First, it achieves optimal theoretical guarantees against these strong adversarial models. So no matter what the adversary does, it obtains very strong error guarantees, these rates, these strong rates. Secondly, in practice, we demonstrated that it outperforms benchmark defenses on state-of-the-art data poisoning attacks on both synthetic and real data sets. Third, it scales very well to high dimensions. So we can run this in very, very high dimensions, and it works fine. And finally, it's very general. It works with just black box access to any learner for more or less any stochastic optimization test. You just plug it on top of any non-robust learner, and sort of it just automatically makes it robust. Of course, there's caveats here, but this is generally correct. Okay, so this is the outline of the rest of the talk. I'm going to first describe this algorithm. I'm going to describe some connections first to a very important primitive called robust mean estimation. I'm going to describe our algorithm, which we call Sever. I should have said that. And then I'm going to give a very high level, like a bird's eye view proof of correctness. I'm going to demonstrate its results on empirical evaluations, and then finally I'll conclude. Okay, let's get started. So before I really get into how we do this, let's make a tangent into a very important subproblem called robust mean estimation. Okay, so robust mean estimation is a similar setting, but a simpler setting. We again have a distribution, but now over just RD, so just distribution over data points. And say it has some unknown mean mu. Okay, and as before, we're given samples from this distribution, x1 through xn, which are drawn uniformly and independently from this distribution, except in epsilon fraction of them again are arbitrarily corrupted. So just like in a robust stochastic optimization setting. And now the goal is simple. The goal is simply to find some estimator mu hat, which minimizes the distance between mu hat and mu, say an L2 distance. Okay, so this is just robust mean estimation problem. It's a very standard, very natural problem. It's been actually studied since 60s and 70s of work of Hubert Juki. But actually it was not until very recently that we were able to get efficient algorithms for this problem that got optimal statistical rates in high dimensions. This started, I guess, 2 years ago now, and since the disseminations of those works, there's been a flurry of activity on it, which I don't really want to get into. But let me describe an important algorithm that came out of this, which will be very important for us later on, which we call filtering, okay, which was introduced in the above two papers. And sort of the intuition for more or less all the algorithms, or I guess a large fraction of the algorithms that have recently come out for this problem, is that if the empirical mean of our distribution, of our data set has been corrupted, if it's far from the true mean of the distribution, then if it's large enough, this can be witnessed by the top eigenvalue of the empirical covariance matrix. The top eigenvalue will be too large, larger than it should be. And moreover, when you project onto the top eigenvector, when you project the data onto the top eigenvector, the bad points, the corrupted points that are causing this shift in the mean are generally going to be more correlated with this than they should be. Somehow this gives us nice, simple, iterative algorithms for this problem. So I don't really want to get too much into the details of it, but more or less by using these insights and being careful, you can get the following guarantees. At a very, very high level, if your uncorrupted data is pretty reasonable, it satisfies some nice concentration properties, then this algorithm filtering either certifies that the empirical mean of our corrupted data set is actually pretty close to the true mean, that you're actually not that bad, like the bad points aren't actually corrupting your mean too much, or it'll somehow throw away more bad points than good points with very, very high probability. Okay, so in the latter case, at the very least, you're making quite a bit of progress. Okay. So I don't want to get into how this is done, but this is actually a very simple algorithm as well, and can be efficiently implemented in very high dimensions. So let's see how we can apply these sorts of ideas back to this more general problem of robust stochastic optimization. So here's a reasonable first try. Simply run SGD using robust estimates. What does that mean? Well, recall stochastic gradient descent is the following optimization method. I have some model, theta t, and at time t, I let theta t plus 1 be the current model minus some step size, eta t, times the gradient of fi at theta t, where fi is a fresh draw from my distribution over functions. Okay, and when there's no corruptions or anything, this works good, because the expectation of the gradients is the true gradient of the function at my model theta t. Stated perhaps more suggestively, we have samples, gradient in f1 up to gradient of fn, and all we care about is being able to estimate the mean of this distribution at my theta t. Right? And when there's no corruptions, I can just use a very naive plug-in estimator, just try any one. So when there's corruptions, and if we have this technology of robust mean estimation, a very natural thing is to just, instead of using a plug-in estimator, use some robust mean estimate at this step. Okay. So instead of going in the direction of a gradient, go in the direction of G sub t, where G sub t is some robust estimate for the gradient at your step. And it turns out this works. In theory, it gets optimal rates, but it's somewhat slow in practice. In particular, previously, stochastic gradient descent just kind of, you just look at a single gradient at every iteration. Now to do this, I'd have to look at a lot of gradients to be able to use my robust mean estimation technology. So it's a rather slow process as opposed to before. Also, this requires us to use the stochastic gradient descent optimizer, and I promised you that we could plug this in on top of any black box learning. So this doesn't quite achieve the goals that we wanted. So how do you fix this? Well, here's our idea. This is the main idea of our algorithm Sever, which is to run the filter, specifically use the filter, not just any robust mean estimator, and only do this when you've already approximately minimized the empirical learning loss. So what do I mean? So here's how the algorithm works. It's very simple to describe. Initially, we let S be the set of all training examples, so we assume everything is good. And then until termination, we just repeat the following process. Use any black box optimization routine to find an approximate minima on the current training set. In other words, find a point where the empirical gradient of the risk is 0, or about 0. So find this data, and then just run the filter on the gradients of your functions, evaluate it at this point theta. And now the filter will tell you one of two things. Either it says that we're good, it returns a certificate, and at this point we just output. We terminate and output theta. And otherwise we just throw away all the points that the filter tells us to throw away, and we repeat. Okay? So it's a very simple sort of framework. You just, pictorial model, you have theta, you fit a model, you extract gradients, and then you run the filter, which is just some simple approximate SVD-based algorithm to compute some approximate scores, and throwing away points based on the scores. And then you just repeat this process over and over until termination. Okay? And it turns out that this works. So, ignoring many, many details, here's more or less the idea of why it works. So, recall that there's two cases. Either the filter tells us that we're done, or the filter throws away points. So suppose the filter tells us that we're done. It gives us a certificate of something. Right? So what does it actually do? When you terminate, the filter gives the guarantee that the empirical mean of the data points that you're filtering on is close to the true mean of the distribution of the points that you're filtering on. Well, the data points I'm filtering on are actually the gradients of my models at theta. And the empirical mean of my gradients at this point theta is about 0. That's what it means to be an approximate minima in this context. And the true mean of the good distribution is just literally the gradient of f bar of theta. And when filter terminates, you have a certificate that the two of these are close, which means that the gradient of f bar of theta is approximately 0. So you're an approximate minimizer. Alternatively, if the filter throws away points, then sorted by the guarantees of the filter, and this requires, of course, some work, you can just plug that in and just say that you're throwing away more bad points than good points. And so you're making progress. Eventually, you're going to throw away all the bad points or terminate. That's it. That works. And I'm hiding many, many details here, but this is the very high-level idea of why things work here. Okay, and when you kind of work through everything, you get the following sorts of guarantees. This is data for convex functions, and if f is convex and if the covariance of the gradients is bounded, then under some model assumptions, then with enough samples, you can output an approximate minimizer with these sorts of parameters, and these are optimal. And to be extensive, we can also give results for non-convex objectives, essentially that we achieve some approximate first order minima. Again, the sample and runtime bounds that we get, in theory, are polynomial in general, but not super tight, but for specific things like generalized linear models, you can get tighter bounds, this kind of stuff. Okay, so that's it for the theory. Let me show you how it works in practice. So we tried this for two tasks. We tried this for regression, and we tried this for SVM. Both tasks we did for both synthetic and real-world data. We took sort of the best data poisoning attacks that we knew of, and we just tried them on our defense as well as the other benchmark defenses that we had. Okay, and you can see, and in this case of regression, we just plotted the test error as a function of epsilon, or if epsilon is a fraction of outlier points. And you can see the other benchmarks like L2 or loss or whatever these mean, their error does really kind of blow up as this epsilon increases, but ours sort of stays pretty flat. And even when you target these attacks to do the worst that they can against our defense, which is the third figure, you can see we still do quite well. So this is in the case of regression. There's a similar-ish case for SVM. So here, actually, Jacob has this extensive test suite of attacks that he developed for this previous paper that I mentioned. And we plotted against these, but there are a lot of attacks. So what we did to kind of present the information in a somewhat reasonable way was we took all these huge suite of attacks, and we also took a big suite of defenses that were that Jacob had. And for each defense, we took the attacks that achieved the strongest error against this attack, this defense. And we plotted the performance of all the defenses against this attack. So when you take other benchmarks, you can see that our error is actually quite good. And for the other attacks, for the other defenses, there's always some attack that gets pretty good error against it. But even when you target the attacks against Sever, you get pretty good accuracy. Very comparable to everything else. Okay, so that's pretty much it. There are a couple of future directions that I should mention. So first of all, we were just getting approximate first order minima. This is generally pretty good, but you could ask for more. For instance, maybe like second order or other kinds of things. Another very interesting question is what's happening with these data poisoning attacks on deep networks. There's just we don't actually know any, so that's kind of surprising. I feel like they should exist, but who knows? Okay, that's it.